Okay, this is week 10, class 1, and our last week called Dead Week. And we're going to be looking at the Convair 880 in its air refueling mode, which is category B. The SAD file is C880 catb.sad off of Archangel. And we're going to do a input Q feedback through a gain of 0.67 on MATLAB. That'll be our SAS. And then we will close the outer loop through theta and put the compensator in the forward loop for the second loop closure. The compensator will have a gain, which was shown here as 115, a lag compensator of S plus 0.5 over S, and a lead compensator of 10 times S plus 20 over S plus 200. And then we will convert the compensator, the lag and the lead, into a PID, a proportional, an integral, and a derivative gain, and replace the lead lag with the PID and see how that happens. And finally, then we'll look at the time delay of the system and make any adjustments from that point. We should talk somewhat about type gain for unity feedback systems on the outer loop. The outer loop is going to be a type 0 system because there's a 0 in the Q to minus delta E transfer function that will be canceled by the S that takes Q to theta. Therefore, there will be no integrals in the forward path. That makes it a type 0 system. A type 0 system will follow a steady state input, if stable, with a finite error. A type 1 system, which has an integrator in the forward loop, will follow a step input with 0 error if the system is stable. And a type 2 system will follow, if stable, both a unit step input and a unit ramp input with no error. Now, to make a PID out of the lead compensator 10 S plus 20 over S plus 200 and lag S plus 0.5 over S, look at crossover. This can only be done at crossover if the omega C, which in our case is 20, our bandwidth is 20, is much less than the 200. Because when j omega is equal to 20, the vector phasor will be j omega vertically of 20, and the horizontal part will be 200. So when you add those two vectorially, you're going to get very close to 200 at an angle of 4 or 5 degrees, very small. So what we're doing is we're replacing the S plus 200 in the denominator of the lead near crossover with just 200. And with that substitution, if you drop that S and multiply out the numerator, the PID gains fall out. Proportional gain being 20.5 over 20, integrator being 0.5 over S, and the derivative gain S over 20. Now here's an M file available that takes us through the control system design for the Convair CatB SAD. And we're looking for a bandwidth of 20 radians per second, 45 degree phase margin, and a step response that follows a unit step exactly with no errors. So you need to get your program and run AAV3. So our inner loop is going to look like 0.67 for a zeta of 0.7, and the inner loop, of course, is shown right here, Q to minus del E with a feedback of 0.67 obtained from SIZO tool. That will not. Our inner loop closure is OLTF2, which is the inner loop closure divided by S, and then we have the lead. And from SIZO tool, we see that a gain of 115 will give us our 20 radians per second and our phase margin of 45 degrees. The lag will eliminate the step error. G lag, S plus 0.5 over S, will give us an infinite response at low frequency, giving us high gain at low frequency to follow a step. And the 0.5 was chosen so that the 90-degree phase lag from the S in the denominator would be taken out by 5 radians per second. This has to be done before 20 radians per second, which is the crossover frequency. So S plus 2 over S would have worked as well, since the gain would have been taken out by 20 radians per second. And here's our response. Again, I'm skipping this SISO loop. We can create a PID by eliminating the S in the denominator of S plus 200. So let's take a look at this. Over here, if I were to look at this denominator right here for this transfer function, I can see that when omega is equal to 20, the 200 will dominate. And so if I eliminate the S and set a PID equal to the resulting quadratic product divided by S in the denominator, I will end up with these PID gains as shown here, near crossover, only near crossover. So we can look at the step response then, and we note over here that the step response is a little bit lower than before, and so it actually looks a little bit quite acceptable, and almost overlays the old one. Here are the transfer functions. The original system is shown in red, and the system with the PID or with lead lag is shown in green, and they overlay all the way out to crossover. And here we can see the system without the lag. This divergence at high frequency is caused by the difference between the PID and the lead lag, but notice how close everything is near crossover. So we have duplicated the response near crossover with the PID. That's why our time response looks pretty well. The problem with this, of course, is the delay margin. We're only allowed 0.04 seconds, and we want around 200 milliseconds, right? So that would be 0.2 seconds. If, however, I were to lower the bandwidth to 2, and SISO tool tells me to do that, I would use a gain of 2. So then I could close a second loop, or a different loop, lowering the bandwidth, and now I would end up with 0.6 seconds and a slower response, but one that might be acceptable. So since the delay margin is acceptable, once again we see how the convergence occurs near crossover, which is the closed loop. This is the closed loop Bode plot. It shows us we lowered the bandwidth till 2. Since we've done that, maybe we could have changed the PID. So in other words, if I look at my lead compensator, we removed the S at 20. Well, if we removed the S at 20, we certainly could remove it when omega equals 2. So this would certainly look like 200 when omega equals 2. But so would the numerator. So the 20 is going to dominate the numerator at a bandwidth of 2 as well. So if 2 is my new crossover, it looks like I've got 10 times 20 over 200. So it looks like the entire lead compensator is going to look like 1 at crossover. Therefore, can I get away with making my PID just 1 plus 0.5 over S, which is what happens with the lag compensator. When this becomes 1, then my S plus 0.5 over S gives me a proportional gain and an integral gain. I have no derivative gain. So I just have a PID that acts as a lag compensator. Let's see what happens. Again, with a gain of 2, here's the difference between the original system that we lowered the bandwidth for with the PID, the full PID, and the system with only the lag compensator. Now the lag compensator may give us a little problem with the steady state error, but you see the responses are pretty good. And the lag compensator by itself gives us 203 millisecond delay margin. So we could have a time delay of up to 0.2 seconds before the system would go unstable. Here's the closed loop Bode of the system with the PID acting as a lag compensator, or the lag compensator by itself. And again, I see up until the bandwidth of 2, the systems basically overlay with each other. And this ends the M file. Note the trade-off that occurred between the specification for each loop closure, depending on how I was changing the lead or the lag. And of course, almost everything depended on the crossover frequency or the bandwidth that was chosen at the end. So this underlines the fact that you don't want to have a higher bandwidth than is required to do the task. And a lower bandwidth pays you a lot better benefits in giving you more tolerance for any time delay.